This is a typical Chinese Apple knockoff USB charger. It's the square pin version for the UK, and it came from a company called Banggood online, who are just an absolute delight for Chinese stuff. Now this one cost a staggering $2. Seriously, $2 for a USB supply? And I got one just to take to bits. Now, it arrived very quickly. It arrived within 10 days, and it came, so I could fit it into our square pin sockets, it came with a square pin adapter. No, I'm not 100% sure why they did that. But anyway, they did, which was very nice of them. So this thing is rated 5 volts at 1 amp, and it's theoretically rated 5 volts at 1 amp, and I tried testing it. I tried testing it with a very rough setup of this, and first problem. This is a digital readout in the front, so I thought, like most USB supplies, they usually do point in the same direction, so I rammed it in, and it appeared to be dead. I didn't actually realise that this one makes the display face back to front, but it still went in and just folded the inside up in the opposite direction, so false start there. But anyway, once I'd sorted that out, I plugged it in, and I plugged in this USB splitter and this hub, and I plugged in 4 of these lights, which take roughly about 150 milliamps each. But I have to say, I'm not overly sure about the accuracy of these units, and I'm pretty sure they drop a small amount of voltage across these. Well, they must, to sense, of course. And this also seemed to be limiting, so I wasn't able to really 100% get a good accurate test. The voltage in this started off at 5.3 volts and it went down a bit. However, that's not what we want. We want to open it. So let's open it and see what it's like inside, particularly the isolation from the mains. So what's the best way to open this? Is it this? Yes, that's the best way to open it. It is held together quite strongly, I have to say. Now, first surprise, the circuit board is single-sided, and there's no chips or anything on it other than this opto-isolator. And the circuitry is really simple. I mean, there's 2 electrolytics, 2 small capacitors, there's 4 resistors, a zener, and 2 transistors, and a couple of diodes. That's it. So I reversed engineered it, and it looks like this. The mains comes in through a diode, charges up this capacitor, the main smoothie capacitor on the main side, to it's 2.2 megafarad 400 volts, so it goes up to about 330 volts DC on our main supply here in the UK, which is 240 volts. Then the primary of the little transformer here is switched through the, I was going to say power transistor, but all I'll say about this transistor is it's a high voltage transistor. It's still in a TO92 package. It's a tiny little thing. So the primary is switched from the positive 300 volt side through this transistor to the negative side with this inline 12 ohm resistor, and I'll come back to that later. The feedback for that, it's a very simple feedback circuit. The transformer has 3 windings. It's got the primary, the secondary for the 5 volts, and a feedback winding down here. The feedback winding feeds back via this capacitor through this 680 ohm resistor to the base of the transistor. And to start it going, there's a very high value, 3.6 mega ohm resistor, that in a power up state, this will just trickle enough current to start turning this transistor on. As soon as it starts turning on and current starts flowing through this, it starts an avalanche effect, and it starts driving itself from this feedback circuit. Now, the capacitor there, I'm guessing that's just to limit the on time. I guess it means they can fine-tune the oscillation frequency. I'm not 100% sure. But anyway, the reason for this resistor here is current regulation circuitry. Whether it's due to the output being short-circuited, or, which I haven't tested, or maybe it even comes into operation in each half, on each cycle of the oscillation. But if the current through this whole circuit exceeds about 50 milliamps, you'll get roughly 0.6 volts across this 12 ohm resistor, which will then turn this transistor on, and that will shunt the power switching transistor down to ground and it will turn it off. The other way that transistor can be turned off is with this opto-isolated transistor, which is coupled to this LED over here. So let's look at the secondary side now. The secondary winding is rectified through this diode and charges this 220 microfarad 10 volt capacitor, and that puts the 5 volts out to the USB port. The LED in the opto-isolator is connected in parallel with a 470 ohm resistor, and I'm guessing that's just for stability for the Zener here. And when the Zener's voltage will be rated for 5 volts minus the forward voltage of this opto-isolator LED, so that as soon as about 5 volts is exceeded, this Zener starts conducting this LED lights, which then couples over to this transistor at the primary side, and it just shunts the base to the emitter of this transistor and turns it off and stops it oscillating. So it's a very simple circuit. It's really quite neat actually. There's a decoupling coupling capacitor here for RF interference reasons that couples the low voltage side to the main side. I'm always a bit wary of these, but then I'm also wary of the insulation of the windings, and also a bit wary of the isolation of the circuit board. Now it's not bad in this unit. It does at least kind of identify a track here. Now I've got a picture of this somewhere. Here we are, which I was using to decipher the whole thing. And it's got this isolation route here, which is barely more than 1 millimeter. It's quite small. And that's not really 100% compliant with electrical standards, because if you consider that these pads here are the USB shell, which would often be connected to the negative, which it is here. If you consider that, then this track comes very close, within just barely over 1 millimeter from the main side via a diode. So, you know, it's not really good enough isolation. It makes you think of that instance in Japan where the air hostess was electrocuted by her phone. And that's the sort of thing that, you know, it could have been moisture getting into it, it could have just been tracking across, it could have been a solder splash, or it could have been the isolation of these transformers, because I'm not 100% sure how good that is. Looking at it at the moment, it looks as though the secondary is wound possibly on the outside. I'm not 100% sure without stripping that transformer to bits. But on the other hand, it's quite nice that they've included this opto-isolator. There is proper feedback. And underloading the voltage, it started off around about 5.3 volts and it did drop, but not a huge amount. I would have guessed that 500 milliamps is what I'd be comfortable running a power supply like this at. But yeah, you know what, for $2, it's surprising. Oh, and here's another thing, the 2 transistors in it aren't some special anonymous transistor. The Q1, the one that's actually switching the primary, is a 13001, and I looked it up and it's a readily available transistor. And the little current regulation transistor is a S9014, which is, again, it's just a generic NPN transistor. This one's rated for 400 volts, this one's rated 50 volts. It's all just common components, and you know, no surface mount, just all on the surface stuff. And as designs go, it's, you know, quite surprising. It's actually better than I was expecting. Not sure if I'd be confident in trusting my life on it, but for things like a USB power bank, where most of the things, you know, you can treat everything metal as all being live, it's not bad. It would work. I wouldn't really want to plug any expensive USB charged appliance into it, but you know, it's not bad. It's not bad at all.